Welcome to EDU World Space.
So here we'd like to find what p-values make this series convergent. So let's apply the integral test. So we can define f of x as ln x over x to the p, and here you see n is at least 1, so we'll take x to be at least 1. Now to apply the integral test, we have to make sure that the hypotheses are satisfied. So the first one, f of x is positive if x is bigger than 1, and we can see this because natural log and x to the p are both positive. And if you divide two positives, it's still positive. Further, we need that f of x is monotone decreasing. And perhaps the easiest way to show this is to just compute the derivative of f and show that it's negative. So here you would just use the quotient rule and then show that it's negative if x is larger than 1. And if you have to apply a bound on p, that's fine too, but you shouldn't have to here. Okay, now using the integral test, we look at the integral and here let's go ahead and do a u sub. We'll have to be a little bit careful here because right now, and also this 1 becomes, this 1 over here becomes natural log of 1, which is 0. And then we have, if I write u du, that gives me ln x over x dx, but I need x to the p. So we have x, so we need another x to the p minus 1 factor here. And here's how we'll obtain that. So exponentiate both sides of this. And then raise both sides to the p minus 1. And there we go. So we'll put that, instead of writing x to the p minus 1 in the denominator, we'll write it in this form over here. Now we've ensured that we haven't changed the integral. And let me just go ahead and write this as just put a negative on that p minus 1. Now this is the integral that we'll deal with. So let me rewrite that. Okay, so this is an improper integral, so we should probably rewrite this as a limit before we integrate. Okay, so we'll deal with the limit at the very end. Now we have to integrate this on the inside, and here I'd use integration by parts. So using parts here will give us the following. And then we have our limits, 0 to k. So then the next step is just to go ahead and plug in those lower and upper limits, 0 and k, in for u. So that's when you plug in k, and then go ahead and plug in 0. The first term just becomes 0. So clearly we can see that we should not be taking, so far we are considering p not equal to 1, otherwise these denominators wouldn't make any sense. So p equals 1, we'll deal with that in a moment, but let's not worry about this case right now. So right now we're assuming we're in this case so that all these fractions are defined. Now let's consider two cases. So p is not equal to 1, so we have either p less than 1 or bigger than 1. So let's assume for the time being that it's less than 1 and see if the integral converges. So if p is less than 1, that implies 1 minus p is positive. And then, so now when you take the limit as k goes to infinity, this first term right here will go to, well, k is going to infinity, and then you have a positive number times infinity, so that's also e to the infinity, and that is just infinity. So that'll be divergent. On the other hand, if p is larger than 1, then 1 minus p is negative, and this is a good thing because now this becomes infinity, but now we have e to the minus infinity because of the negative, the 1 minus p being a negative. And this limit, if you rewrite this, so now I'll write it as a p minus 1. P minus 1 is positive. Just multiply this by a negative. And use L'Hopital's rule. L'Hopital's rule here, because it's infinity over infinity, and you will get 0 here. And similarly, this is e to the minus infinity, so that will go to 0. And we have a bunch of real numbers that we add, and this will converge. No infinities at the very end. So it will converge. So we're mostly done here. Now on the next page, we'll just have to deal with the case where p equals 1. So if p is 1, in this case, just go back to the original series. Now, this is bigger than this sum here, so perhaps I can be more formal here, so let me go back. So n to the p just becomes n. Now let's plug in the first few terms. ln of 1 is 0. And so on, and then let me rewrite this as and you'll see why I'm pulling out the 3 in a second. It's because of the following fact. If n is bigger than or equal to 3, then natural log of n will be bigger than or equal to 1. So this series is larger than the harmonic series. So here this diverges. You could either say harmonic series or just use the p-test with p equals 1. And therefore, by comparison test, NP diverges if p equals 1. So therefore, by what we showed on the previous page, the original series converges if and only if p is bigger than 1.